Hello again. Let's go ahead and get on with a lecture, this time on geometry and cost estimation. So financial math, in the sense that we'll be talking about money here towards the end of it a little bit, talk about, maybe if you're trying to build something or something of that nature, then how much will it cost you? Not quite so much financial math in the sense of like loans and investments or anything like that, however. But let's go ahead and get into this. So primarily we're going to be talking about geometry here. We're going to be talking about shapes. Let's go over a little outline of what we're going to see here today. Some of the main things. So we're going to start off. We're going to talk about perimeter. And so if you're familiar with that, that's going to be sort of the length around an object. We're going to talk about area, and that's going to be how much sort of space does the object take up. If it's two-dimensional, I'll go ahead and mention this is 2D, so is perimeter. It's two-dimensional. So maybe if you're looking at just a flat surface. We're going to talk about volume, which again is like area. It's how much space something takes up. But this time we're talking about 3 dimensions. We're going to also, excuse me, we're going to talk about the Pythagorean theorem. It's a mathematical theorem that's very useful as far as triangles are concerned. And then lastly, we're going to wrap it all up with some cost estimation. So kind of like I said earlier, we'll look at, hey, if you need to go out and buy maybe some bark or something like that, how much do you need to buy and how much is it going to cost you? And with all of this, what we're gonna do is we're gonna basically look at all of these things with various shapes, sort of mixed in. So the focus here will be on these topics, but we'll talk about these topics with these various shapes, square, circle, triangle, etc., things like that. So we'll have all those various shapes mixed in into all these topics. Let's go ahead and start with perimeter. So we're gonna have perimeter here, a little header. And so just to look at some examples here, let's say that we had a square, something like that, something pretty simple here. So I'm labeling this P for perimeter, and then with that little subscript square, just to indicate, hey, we're looking at a square here. So if I have something like this, and this is just my square, you could presume that it has a side length of S. And because it's a square, by definition, all of those side lengths are the same. So they're all S. And so this idea of perimeter is basically just saying, hey, you know what? Let's take the entire length around this thing. Pretend you're walking around this square. How far do you walk? Well, in this case here, we would walk a distance of 4S, where S is just whatever that side length of the square is. We could also look at something like a rectangle, which is similar to a square, but obviously not quite the same thing. And on this triangle here, we may have a length and we may have a width. And what we'll notice here is that because it is a rectangle, this side down on the bottom is also L, and this width or this side length over here on the left is also the width. That's what makes it a rectangle. And so if I go and I add all of these up, if I add L and W and L and W, I have two L's and I have two W's. So I add those together and I end up with 2L plus 2W. And so in general, what we're seeing here is that perimeter is just equal to the sum of the outer edges of a shape. So I could even theoretically give you, a shape that's all ugly and complicated like this. Ooh, that's a little bit. Let's make that a little bit more careful. So we could have this really ugly shape here, and what you'd have to do here is you would have to just look at all of these sort of different side lengths here. You'd have to measure all of those. And then once you have measurements for all of those, you would just add them all up, and that would give you the perimeter of whatever that shape is. And so obviously there are more shapes than just, square and rectangle. There's triangles, there's circles, there's all sorts of things. So let's go ahead and look at just two more of them. But a lot of times we'll just have to be clever about how we actually come up with these perimeters. So just to give ourselves two more examples here, let's go ahead and copy this page over one more time. And then we'll actually just erase this square and rectangle. Well, let's go ahead and erase this as well. We've seen that. So perimeter is some of the outer edges of the shape. And so let's suppose that we were looking at an equilateral triangle. So if we have that perimeter, let's go ahead and draw an equilateral triangle. That's going to look like that. And because by definition of it being an equilateral triangle, it has the same length on each side. So I'm going to call that length S, and then we just see that this perimeter is 3S. It's just as simple as adding them all up. Let's look at another example. Let's say we had a circle here. And if we actually draw a circle, let's go ahead and do that. So we have our circle. Oop. That's not good. Okay, that's fine. So our circle is filled in there just a little bit. That's okay. And so what we've got here, we can label some important things here. So first things first, I want to label the center of the circle. That looks about right. So that's my center of the circle right there. And when we have that, that actually gives us two particular lengths that we can measure. What you may be familiar with is this idea of a radius. And that radius is that green distance right there. Go ahead and label that R. And then likewise, what also we have is we have a diameter. And a diameter is just the distance all the way across. I'll put that in red. And so that red length is what we call the diameter. We'll label it D. That green length is what we'll call the radius, and we'll label it red. You'll notice that the radius is just the distance from the center of the circle to the outer edge. And it doesn't matter where you go. I could draw my radius there. I could draw my radius there. I could draw my radius down here. It's always the same. And that's actually what makes it a circle. If this thing is a circle, because all of this outer edge is the same distance away from this point. And so we have the radius there. We've seen what that looks like. You could probably tell that the diameter is just one radius there and then one radius there. The diameter is actually equal to 2 of the radius. So we could actually write that. We could say D is equal to 2 times R. So we've got a little formula right there. D is equal to 2 times R. And that could be useful. So if we actually look at this circle and we think about the perimeter, that's going to be this length around the outer edge there, just looking right around that outside. We actually have a special name for that. We call it the circumference of the circle. And so this circumference, it's just another word for perimeter, but we use it specifically when we're talking about a circle. And we actually have a formula for it that I'm not going to bother explaining too much why that's the case, but it's 2 pi multiplied by R. And remember, pi is that 3.1415. We've got that approximation for pi. We'll say, hey, 3.14. So if I take 2 and multiply it by pi and multiply it by R, that's going to give me my circumference. That gives me the distance around. And then actually what we can do here is we could simplify this a little bit if we wanted to. We can recognize, like we said, the diameter is equal to 2R. So this part right here that's boxed, so not including that pi, that 2r right there, that's just equal to the diameter d. So we could actually simplify this and just say pi times d. Either of these formulas is fine, whichever way you want to remember it, or whichever way I sort of force your hand. Maybe I give you a circle and I only tell you the radius, or I only tell you the diameter. That kind of forces your hand here. But so maybe both are useful to know, but they're really just the same exact thing. There's just this rewriting of d and r for the diameter and the radius. One thing I want to mention just about circles that I think is a little bit interesting is actually this equation here at the bottom where we have the circumference, the perimeter, is equal to pi times d. So we have that right there. We saw this right down here. We've got, hey, the circumference, which is just another fancy name for the perimeter, that's equal to pi times d. What I actually want to do is I actually want to rewrite this equation and solve it for pi by dividing both sides by d. And this gives me this equation here that c over d is equal to pi. And this actually leads me to a little fun story. And this is that how actually mathematicians came up with the value of pi, how they know that pi is 3.141592. It keeps going on forever, obviously. But how they know that this is the value of pi is what they started doing was they had all these circles. They had circles of varying sizes, whether they were, tiny, small little circles, or they were huge circles, just whatever they were. They started noticing that if you measure the circumference of the circle and you divide it by the diameter, so if you have someone walk around the circle and you measure how long it took, how much distance they traveled, and then if you have someone walk across the circle and you measure that distance, if you divide those, they always got the same number. They always got 3.14. It didn't matter how big or how small the circle was. And so they realized, oh, there's this proportion that says that the circumference of any circle divided by the diameter of that circle always is equal to this number pi. And that's how they actually came up with pi. So little fun story there. And we'll move on and away from perimeter with that. So let's go ahead and get into area here. So as we said, area is basically going to be the sort of how much space does an object take up. So let's go ahead and look here. Look here at a handful of examples. So let's start off by looking at a square. And I'm going to draw this right here. So we saw that our square before, it has a side length that we're just going to call S, and it's S all the way around. But here's what I want to do. I want to think about how much space does this take up? Well, what we say here is that you could sort of think of, let's say that you had this as a floor plan in a house, and you were going to put tiles down. And if every tile you had took up, a certain amount of space, this idea of area is just counting how many tiles do you have to put down in order to, in order to cover this space right here. And so with this square that I've drawn in particular, you could probably go through and you count, you say, hey, 1, 2, 3, 4, 5, 6, and you keep going. But that's this idea of area. It's basically kind of like saying, hey, let's place a bunch of tiles down on this space that I have, and let's count how many tiles there are. Well, how we do that can sometimes seem a little bit confusing. And this is where we'll kind of just remember some formulas and we'll just move on from that. So with a square, what we basically do is we walk this length here, and then we walk this. So we walk this length on the bottom, and then we walk this length up, and we multiply those lengths. And so if you ever have a square or a rectangle or something like that, that's how you're actually going to figure out that area. So before I actually go ahead and state what this formula would be, let me go ahead and actually draw this for a rectangle, just so we can see that sort of same idea. So let's say we had a rectangle here. And remember, as we've said with a rectangle, we're going to have a width and a length. This is also a length and a width. Those W's are the same and the L's are the same. So if we were to try and grid this up and try and figure out, where exactly, how do we calculate this area? As I've said, we're going to pretend like we're going to walk across here and we're going to walk up this way. And as we go through that walking right there, we're just counting those lengths W and L. And all we do in these scenarios is we just multiply them. So L times W, S times S for this square. So we can write S squared. And so these are nice formulas for a square and a rectangle. And it's pretty much just like saying, hey, if I were to walk these lengths and I multiply them, that actually gives me the area. Now, at that point, we're kind of just done with the sort of how to find area in terms of like walking. Now it's kind of just formulas. So let's go ahead and look at the area of a triangle. And you'll see quite quickly that just walking around doesn't really help us out here. So if we have a triangle, it doesn't have to be an equilateral triangle like we saw, but we're going to have a height here that I'm going to call H, and we're going to have a length for the base on the bottom that I'm going to call B. And we just have a formula here. This formula is 1/2 times the base times the height. And really what we're getting at here is that if I were to try and tile this, obviously I'm going to use partial tiles here. I'm not going to be able to use an entire tile on some of these parts. And so basically, just without too much in-depth explanation, if you just tiled this whole thing up, it ends up being equal. The number of tiles that you have ends up being equal to 1/2 multiplied by the base multiplied by the height. And so that's just our nice little formula for the area of a triangle. Same sort of idea. If we have a circle, we could draw that. We could say we've got that circle there. And then obviously we have a radius. We've seen that before. Radius of R. And again, if we went along and we tried to tile this, I mean, you could see tiling this is gonna definitely lead to some partial tiles here. So I won't try and tile the whole thing, but I'll just start off here. So you can see that there's definitely going to be some partial tiling. And so again, just without too much in-depth explanation, if you went through and you tiled this whole thing up and you counted it, what you're going to end up getting is you're going to get that number pi that we saw multiplied by R squared. So we're going to square R and then we're going to multiply it by pi. And that's the area of our circle right there. So two more examples for area. We're going to look at the area of a trapezoid. A trapezoid is a weird looking shape. So for our trapezoid, we're going to have a length down there, a length there. And when we actually label these, we tend to label them A and B. And then you'll notice here that the height is just always H. So that height right there we'll call H. Sometimes you'll see instead of A and B, they'll use B1 and B2. I like to use A and B. I think it's a little bit easier to write down. So our formula here is going to be 1/2 times H plus, or excuse me, 1/2 multiplied by H multiplied by A plus B. And that's going to be the area of our trapezoid there. What you should be able to notice here, though, is you could figure out this area of the trapezoid. You could come up with this formula without me even telling it to you. Because what you could do is you could break this trapezoid up into 3 parts. You could break it up into 2 triangles and a rectangle in the middle. And you could just find the area of each of those parts and then add them together, and that'll give you the that area formula that we've got right here. And that's really what we're going to be doing in most of our examples. Is we're going to see complicated shapes that are just broken up, that you can break up into these simpler shapes and use these formulas. Yeah. So another example of exactly what I just said would be a parallelogram. And so if we have a parallelogram, this is actually going to look like so. So it's kind of like a square. Let's make sure that's straight. It's kind of like a square, but it's shifted onto its side a little bit. We're going to have a length B standing for base. I'll note that that length is the same here. And then we're going to have a height here. Draw that dashed right there. Notice that I do not care what this length is or this length. That does not matter for the area. Our area is just B times H in this scenario. And so that's a parallelogram. But again, you could break this up into different parts. You could break it up into a triangle, another triangle, and then you have your rectangle right in the middle, right there. So you could come up with that formula on your own. You could sort of prove that if you wanted to. All right, that's area. Let's go ahead and move on to volume here. So put another header, volume, and we're going to be looking at three-dimensional shapes. So you'll notice that back on the area, these are all two-dimensional shapes. These are all maybe like floor plans or something like that. Versus volume is going to be some object that actually takes up a physical amount of space here. So let's go ahead and look at some simple ones first. And I'm really just going to label side lengths and just give us these formulas. So if we have a cube, we'll be careful here and note that a cube actually has the same side lengths all the way around. Got to be careful as I draw this. So that's our cube there, and it has a length, a width, and a height, and they're all the same. We're going to call them all S. And so the volume of our cube is going to be kind of similar to how we saw before. We're going to walk along this way. Hey, that's S. We're going to walk along this way, say, hey, that's S. We're going to walk up this way and say, hey, that's S. So we multiply them. That gives me my volume for my cube right there. We could have a very similar looking shape that's not perfectly a cube. We'll call it a rectangular solid. What I will mention is that a lot of people call this a cube when in reality it is a rectangular solid. Think like a Rubik's Cube. That's actually a perfect cube because the side lengths are all the same. But what I'll draw here, what you'll see, is that this is an example of where these side lengths don't have to be the same. They could be very different. And so if they're different, we don't call it a cube. We call it a rectangular solid, although some people tend to just use the word cube just to be quick with it, but not quite a cube, rectangular solid. And it, again, in this idea of walking these sort of directions here, it's length times width times height. How you could think about this is maybe tough to imagine, but you could think of like a tiny little cube in here that would take up a certain amount of space, and I'm not drawing that well. So you could think of a tiny cube that just takes up space here, almost like just a tiny little block. And then the question would be, okay, how many blocks does it take to fill up this entire volume that we're looking at, right? We're trying to fill this entire thing. How many of these blocks does it take, right? And then I could have these blocks and I could put them in here and just say, hey, how many blocks does it take? And that's just what volume says. And we have formulas for a quick way of doing that. So we'll get rid of that little green block. We don't need to see that. We'll move on to a little bit more complicated, but not too complicated here. We'll look at a sphere. So this is just a three-dimensional circle. The formula is complicated, 4/3 pi r h. Let's go ahead and look at what the shape actually looks like before we dive into this formula, though. So for our sphere here, we're going to have that right there. And then just making this look a little bit three-dimensional. So we've got that right there. And what you could probably tell is there's still a radius in this. There's still a radius from the center of that sphere to the outer edge, if you will. And so that radius is going to tell us what the volume is. We can just use this formula 4/3 pi r cubed. And it's just given by that radius there. Let's go ahead. I want to give myself a little bit more space here. So we've got all that. Let's do another one. So let's look at a cylinder. Just to be clear as well, this cylinder that I'm about to draw, its formal term is a right circular cylinder. For our purposes, if I just say cylinder, this is what we're talking about. But in reality, it's called a right circular cylinder. And it's basically just any old cylinder that you would expect. I like to use the analogy like a can of beans or something like that. So what you can see here is we have a height h right there, and then we still have a radius r, sort of squeezed in right there. Notice too that is also r. So this length right here that I'm highlighting and that length, they're both r. This just doesn't, this is actually a circle. I'm just sort of tilting the object so it doesn't look perfectly like a circle there. But this is, in fact, a circle. And when we have r and h, we can come up with our volume formula of pi r squared h. We've got some other, two others here, two other common things that we'll look at. The first is going to be a cone. So think like an ice cream cone, but in this case, how I'm gonna draw it inverted. I'm gonna draw it sort of like an upside down ice cream cone. So we've got our bottom there. Let's actually draw that differently. Let's draw the top first. So we've got that right there, and we can still see we have a height h and we have a radius r right there. And so our equation for our volume of our cone is very similar to the cylinder. There's a pi r squared h in there, but we actually just have a 1/3 in front of it. So very similar to the cylinder, but it's kind of like, because we're not worrying about all of that, filled in right up there, we have to multiply it by a 1/3. Lastly, we're going to look at a pyramid. Again, we're going to see this 1/3 length times width times height. And this is going to challenge my drawing skills here. Let's try and do this. Ooh, let's be careful here. So we've got that for our bottom. And then if we were to bring all of this up to that point, like a pyramid, there we go. That looks all right. You can see that we're going to have a length and a width, but unlike over here on our rectangular solid where we could just walk across and we just come right up that height right there, now our height is actually kind of in the middle. It's right in the middle of that pyramid. Let's draw that dashed right there. That'll look a little bit nicer. So that's our height right there, and that gives us the volume of the pyramid. 1/3 length times width times height. Awesome. So that's perimeter area volume. That's super helpful right there. Let's go ahead and get into Pythagorean's theorem. I promised we'd talk about that. So let's give ourselves a label. Pythagorean's theorem. The very first thing that I want to mention here is that Pythagorean's theorem is used for triangles, but it's only used for a specific type of triangle. And that type of triangle is going to be what we'll call a right triangle. Ooh, that doesn't look very right. Let's draw that. So when I say a right triangle, what I mean by that is that this angle here, this angle right there, is 90 degrees. And then these angles can be whatever they want. But this angle here has to be 90 degrees. When we say that, that's what we mean by a right triangle. We call it that because we use the word right because this is a right angle. If this angle is 90 degrees, it's a right angle. So what I'm going to do is I'm actually going to label these sides as A, B, and C. And then let's actually go ahead and say that a little bit explicitly. So A and B are our sides. What I will note is that you can flip those. It doesn't matter. A doesn't have to be the bottom one, and B have to be the one on the side, the one on like the left over there. A and B can be whichever sides you want. It doesn't really matter there. C, we're going to call it the hypotenuse. And that C is what we'll notice here. It's always going to be the longest side of that triangle. C, it has to be, by nature, just that it's a triangle. It has to be longer than A and B. You could try to draw a triangle where that's not true, and it just wouldn't happen. So what Pythagorean's theorem tells us, and this is a pretty awesome theorem, it's very useful. We're going to use it a lot, that's for sure. It tells us that A squared plus B squared is equal to C squared. And so let's make sure we highlight that. So A squared plus B squared is equal to C squared. And so that's basically giving us a relationship between the lengths of the sides of each side of this triangle. We know that if I take each side and I square them and then I add them together, that's going to give me the hypotenuse squared. And yeah, so that's a super useful formula. What I will note, there are certain triangles that pop up quite often. A 3, 4, 5 triangle pops up a lot. And then a 5, 12, and 13 triangle pops up a lot. And really what I mean by this is that if you actually look at this formula, if you do 3 squared plus 4 squared, let's go ahead and write this out a little bit. If you actually do 3 squared plus 4 squared, you actually get 9 plus 16, which is equal to 25. And you'll notice that that 25 is equal to 5 squared. And so this triangle satisfies the Pythagorean theorem. That's good. And then same here, 5 squared plus 12 squared is going to be 25 plus 144, which is 169, which happens to be equal to 13 squared. And so again, we're seeing that, hey, this Pythagorean theorem works. So these triangles pop up a lot. If I ever gave you a triangle like this, 3 and a 5, and I said, hey, what is this? What's this length right here? You could just look at it and be like, well, it's 4, because we know these special triangles pop up a lot. You wouldn't have to show all that work solving for it there. So that's Pythagorean theorem there. Let's go ahead and actually get into an example here where I'm going to give us a parallelogram and we're going to find the area, and then we're going to say, hey, let's paint it. Let's figure out how much it's going to cost to paint it. So let's go ahead and, like I said, we'll start off with our parallelogram. So example, find the area. And I give you this shape right there. And let's go ahead. I'm going to give us this length here of 5, and then I'm going to give us this length here of 10 up on the top. And let's go ahead. And also, actually, I'm going to give us a length here of 6. And I'm drawing these green dash just for our own help. We'll see how we'll see that those are helpful in just a second. So we've got 10, we've got 6, we've got 5. That's fantastic. What we can do now is we can actually to find this area. Remember, we have our formula for the area of a parallelogram, which says area is equal to base times height. And so we could just look at this and we could say, okay, well, our base is 10, right? That's that length across. But the question is, what is our height, right? We don't actually know what this green height is. We have our base of 10 right there, but we don't know what this height actually is. And so we got to figure that out. So what's going to be helpful here is actually using Pythagorean's theorem. And so I want to make note of a couple things here. I want to make note that if this length here is 10 and this length is 6, then this length across here has to be 4. So what I'll note here is that this is 4. You know, that's kind of squeezed in there. Here, let's do this. Let's bring that up. So this length right here is going to be 4. And now when we look at this, what I notice here is that I have a triangle right here where I know that one of the side lengths is 4 and the hypotenuse, that diagonal, is 5. So I have a hypotenuse of 5 and a side of 4. You might just be, sort of shouting out right now, hey, this is 3. This height has to be 3 right here. And you're right. But let's go ahead and actually show that. Let's actually prove that right now. So if we go ahead and we look at this work, we're gonna say a squared plus b squared equals c squared. And remember, c is the hypotenuse, so I'm gonna put my 5 in for that. And then, as I said, it doesn't really matter if I put a as a or b as 4. It doesn't really make a difference here. I'm just gonna say b is 4 and then say, hey, we're trying to find this height, which I'm gonna call a. And so I have a squared plus 4 squared equals 5 squared. We can just start doing our algebra. 4 squared is 16, 5 squared is 25. Subtract 16, we get a squared equals 9. So then when we square root both sides, we're going to get a is equal to 3. And so that tells us that this value of a is equal to 3. And in fact, that's our height right there. That's the height that we're looking for. So when we have that right there, that's 3. And we can just plug that right in. 10 times 3, and we get 30 right there for our area. And what we might want to do here, I haven't written out a fully composed problem statement, but let's say that let's go ahead and do that. We'll say area, and then I'll just put like dimensions in feet, just so we have a unit to use. So our dimensions are in feet. So this area, let's actually be more explicit here. So this area is actually going to be 10 feet multiplied by 3 feet. And so what we say here in our units is we say that this is 30 feet squared. And so that's going to be our area. Our units are in square feet. You may have heard that a lot. If you're doing a floor plan or something like that, or you're looking at the size of a room, you talk about the square footage. You talk about it's 800 feet squared. It's 800 square feet. So that's going to be our units right there. So we've got 30 square feet here for this parallelogram. Now let's go ahead and look at another example here. We're just going to continue this example. Let's say that we wanted to paint this parallelogram. Maybe it's a floor plan in a room or something like that, or a wall plan or something like that. And we want to paint it. So if we actually go ahead and do that, I'm going to copy this parallelogram over. Let's erase some of the things that we don't need here. So we've got that right there. I'll go ahead and label, hey, area equals 30 feet squared, 30 square feet. And our example here is paint the parallelogram? Well, if we're going to paint this, we should know how much it costs to paint it. And what we know is that if we go down to, a local hardware store or something like that, paint costs $3 per square foot. And so now we want to find the cost that it takes to paint this. Well, we can just have our formula. We can come up with a formula here. We can say, hey, the cost is going to be equal to the area of paint multiplied by the cost of paint per area, right? And so what we'll notice here is if we actually just sort of plug straight in here, the area that we have to paint is 30 square feet. Well, then they tell us that it costs $3. I'm going to write this a little weirdly here. $3 per square foot. And so we actually have some cancellation here. Our units here and our feet squared will cancel. And so really what we're doing, I mean, this should make sense. We're taking, hey, I got to paint 30 square feet and it costs $3 per every square foot. So every one of these 30 square feet that I want to paint is going to cost me $3. And if you keep adding all that up, and in our case here, we'll do it quickly by just multiplying, you're just going to get $90. And we can go ahead and we can just put a dollar sign right here. It's going to cost $90 to paint this parallelogram. And it's really just that simple multiplication right there. But I really want to emphasize this units that cancel. We don't have our feet squared anymore because we have feet squared divided by feet squared, they cancel, and there we go. So we get $90. There we go. We found out how much it costs to paint this parallelogram, and we're all said and done. So that'll be it on this geometry and cost estimation lecture. We'll call it there.